Look okay? Okay, sorry about that. And I can't, with this, I don't think I can see the chat. So if someone has a question, maybe if someone else could point that out. So I'll get started. Thanks, everybody. I'm going to talk about DClaw, which is software for granular fluid problems. So what is DClaw? Well, it's really the difference between DClaw and GeoClaw has to do with the model that's solved. And in DClaw, a two-phase system for granular fluid mixtures is solved. It's still a depth average flow over topography, so it's like the shallow water equations. But for the applications we look at with DClaw, it's originally developed for landslides and debris flows. If you're not familiar with debris flows, they are just highly mobile, typically liquefied landslides that travel long distances. But we can also look at overland flooding that entrains debris from the bed below the flow, and also dam breaching, earth and dam breaching, where you have a lake that overtops an earthen dam and then begins to entrain that material. We can also look at landslide generated tsunamis or lake inundation by landslides or lahars. Lahars are just a type of debris flow on volcanoes. And also I should have here, I noticed Harry A was watching. I should also include here tsunamis that entrain debris as they come on shore. So in terms of software, DClaw is, you could think of it as a subset or an extension of GeoClaw, but it's currently based on an older GeoClaw code. So it forked from GeoClaw over 10 years ago, and so a lot of the features in GeoClaw are present in DClaw, but some of the newer developments are not there. And eventually, we'd like to change this, but that's the way it is now. Can you guys see my mouse pointer with the way I have this?
Yep.
Okay. So currently, I have DClaw at this GitHub site, GeoFlows, and there's a DClaw repository where you get the actual source code. And then I've also set up another repository for application examples called DClaw Apps. Okay, so just a brief model summary. I'm going to go through a little bit of the background of the model and then show some examples and give some ideas of how a simulation's set up. So the solution, which I'll use Q for the solution like we typically do. The solution variables are like the shallow water equations in that we have the depth, the flow, and the momentum. But in addition, now we have the solid volume fraction, which I've denoted M. So the variable solved is the depth times the solid volume fraction. And then we also solve for the basal pore fluid pressure. And so for landslide and debris flow dynamics, these two variables, the evolving solid volume fraction and the fluid pressure of the interstitial fluid between the solid particles, are important variables that regulate the mobility of the landslide. Let's see here. Yeah. Okay, so just briefly, where does this model come from, or what does it develop from? It's really sort of an integration of some different areas of fluid dynamics and solid mechanics, and as well as soil mechanics. If you want to see all the gory details, it's in this publication here. But I'll just point out one of the aspects of the model that's important is this evolution between the fluid pressure and the solid volume fraction. So I refer to this as I'll go back here, a two-phase model, but you might notice there's only really one velocity phase here, and that's for the mixture. But the the important solid fluid coupling or effects are through the fluid pressure and the divergence of the solid volume. So there aren't explicit drag terms between the fluid and the solid because we just have one velocity field. But we do model, because we model the solid volume fraction and the divergence of that solid volume fraction as the material contracts or dilates, that affects the pore fluid pressure. As the pore fluid pressure rises, that reduces the effective stress, the frictional Coulomb stress, and the flow can become more mobile and behave like a fluid. as the material dilates, that drives down the fluid pressure, increases the effective stress, and one can have a landslide that slumps and then stabilizes. And so landslides and debris flows exhibit diverse ranges of behaviors and in terms of their mobility, and that's due to this coupled evolution. In terms of what informed the development of this model, an important validation tool is the debris flow flume, the USGS debris flow flume. So you can see here it's this long 90-meter channel that's heavily instrumented, where we can measure depths and pore fluid pressures and different metrics of the solution. Up here there's a head gate, and you pile sediment essentially behind that, open it up, and let the debris flow landslide flow down the flume. I mention this also because the examples of setting up simulations at the GitHub site, the flume here is probably the easiest one to use because the topography is synthetic. You know, it's easy to create this topography synthetically. So you can, that's an example you could try to run without needing topography DEMs. So with DClaw, we can simulate these experiments that are done at the flume. I'll briefly mention this. There are other types of experiments that don't have they're not gate release, that are more like a real landslide or debris flow, which begins not with the opening of doors, but by the changing pore fluid pressure in the granular fluid mixture. So this is something we call natural release experiment. So in this experiment, this debris prism was set behind a retaining wall. So in this cross-sectional schematic, this wall is here. There's debris piled behind it, and in this experiment, then water. This is watered with sprinklers and channels beneath the bed, which increase the pore fluid pressure. Eventually, that pressure gets to a point where the driving forces overcome the decreasing frictional resistance, and the material flows over the wall. So in this simulation here, you'll see this blue line. That just indicates the rising pore fluid pressure, which we're just manually specifying in the simulation at the start as representing watering or any other process which would increase the pressure. So I'll point out that with landslides, and it's difficult to determine simply from the initial force balance what the outcome will be. And so I'll back up here. If I'm referring to this as loose soil, we have this soil behind the wall, which is placed there at a given initial solid volume fraction or porosity. And if we repeat the same experiment, but this initial sediment is compacted just slightly, so reducing the porosity by just a few percent. If you look at the time scale here, this simulation, we reproduce the exact same initialization process as before, but as this pore fluid pressure rises, the material actually fails here at what I've defined as T equals 0. But 60 seconds later, you can see it's still just sitting here. You can't really see what happened, even though material did begin to move. And so initial conditions with respect to the material are an important part of what the eventual outcome will be in a simulation. So moving on to more realistic problems in the real world, and really what DClaw was developed for, is modeling landslides and large debris flows that might occur off, for instance, Cascade volcanoes. So here's an example of Mount Rainier, and we're looking at hypothetical landslides and debris flows or lahars there. So in this example, these are hypothetical landslides which we modeled, which may evolve into rapid debris flows. And here you're looking at the western side of Mount Rainier. Here's our material that's going to fail. So one has to start out in DClaw with specifying the landslide material that'll fail. it's DClaw, you can do some slope stability calculations, but it doesn't create the failure surface or this basal surface below the material it'll fill. That has to be specified. So how is that done? Well, I'll play some animations here. So this is the same setup here. We initialize this material here and raise the pore fluid pressure initially until the material fails, and then we let the equations take over and the debris flow evolve. So this, did that animation come through okay? Okay.
Yeah, fine.
Okay, thanks. So this is looking down now at a map view of the same simulation, and you can see the landslide here, Mount Rainier. This domain's pretty large. I don't have a scale here, but the Puget Sound and Tacoma's up here in this corner, and we let it flow. So of course we're using the same patch-based AMR that's in GeoClaw, which the evolving grids that track the flow as it moves down these winding valleys. And so AMR is used a little bit differently than it would be in say a tsunami simulation, where you might refine a great deal near the shoreline, and you might have very different resolutions for let's say waves in the deep ocean. For debris flows and landslides, we're really using AMR more just to take advantage of the complicated evolving domain. So it's kind of like trying to use a mesh that fits to where the flow is going, essentially. And typically, the same refinement level will be used for the flow everywhere. So I typically am not refining a great deal in different regions where there's flowing material. The AMR is used just to capture where the debris flow is going. So how do we initialize something like this in terms of setting up a DClaw simulation? So this is looking at this same landslide, and here's a figure here showing the side of Mount Rainier where this source is. It's in the Sunset Amphitheater region. And so first we identify a region where we expect the landslide to originate, and that might be based on outside data, based on subsurface characteristics or slope stability models. And then using that, we then construct a basal surface below the landslide material. So the landslide material then initially is defined as the material that sits on top of this basal surface which we constructed, or this failure surface. And so let's see, here's another example. This is a different landslide. This is the Oso landslide in Washington, but you see we identify here a region where we want where we expect the failure to occur. We might look at transects, longitudinal transects that region, and then create the failure surface which sits below the top surface. In this example, these are the different transects here, and these are 3 different examples of failure surfaces with different volumes. So often we'll identify a volume we might be interested in, and then these lower surfaces satisfy certain conditions which are typical or somewhat physically realistic for landslide scarps and failure surfaces. So one thing that's maybe slightly, well, not counterintuitive, but sometimes causes a little bit of confusion is the topography. So like in a GeoClaw simulation, you're usually thinking of the topography DEM as your basal surface. And it is here too in terms of DClaw for most of the domain. But for the landslide source area, your topography DEM actually is the top surface of your landslide. And so what you might think of as the basal or topography surface in the simulation is created, and your external data, your DEM from LiDAR or whatever source you have, is actually the top surface then. And so setting up a DClaw simulation, we have to initialize those variables up. So just like GeoClaw, set run.py is the routine where a lot of this is set up. And so in that routine, you set up the computational domain and so forth. And then we set up topography here. And so I don't know if I'll go through all these details here, but these slides will be available if you want to look at how these are set up. But for instance, in this example, when we input our topo files, remember that we've got topography for the domain, but then we also have, so this here might be our LiDAR DEM or some other DEM we get. And then our landslide slip surface we read in with the DEM file. So here would be a DEM that represents topography, but it's the basal slip surface. And then you might also, like a GeoClaw simulation, have some part of the domain where you have a really high resolution file or something for some location of interest. And then to initialize the actual landslide, so here, remember, we've just set up the basal surface. And then often your landslide source material comes from some current DEM that's specifying the top surface of the landslide. And so in setrun.py, there's a feature in DClaw that's similar to the topography files in GeoClaw, except I've called them QInit files because we're initializing Q. And so much like reading in a topography file, we create this list of lists, and it has similar variables here to GeoClaw. But notice there's this second term here specifies what component of the solution you're initializing. So when you look down here at this, where we read in, where we specify this QInit file, I've set QI equals 1, which goes down here. And so this file then specifies a depth. Since landslides initially, there's complex geometry, spatial geometry of your initial variables, DEM files are used for setting up essentially all the variables in DClaw, except that you can have defaults. So for instance, the initial velocity is typically 0 and so forth. Usually it's more typical to have a DEM of the top surface rather than the depth here. And so one can also specify the initial landslide by reading in a file that has that top surface. This is a bit confusing, but notice our solution here doesn't have eta as one of the variables. So just a convention that I've used is to denote the QI component that you're reading in for eta to be 1 plus the number of equations here. Okay, so I'll move on from that. But a lot of these details, if you have questions, if you want to try out DClaw and you have questions, let me know. So I'll kind of move on to some more recent things that we're using DClaw for, and that's where we have granular fluids like a landslide or a debris flow, but it may also be interacting with the body of water. So remember, DClaw is two-phase and spatially varying volume fractions. And in the DClaw equations, if the solid volume fraction goes to 0, the equations reduce to the shallow water equations. So essentially, you could model tsunamis with the DClaw equations. It wouldn't be as efficient as just using GeoClaw, but theoretically, it's the same when the solid volume fraction tends to 0. And so we model landslide-generated tsunamis, for instance, by creating the right initial conditions for a landslide and a body of water. We can look at debris flows entering lakes, landslide-dammed rivers, problems like that. Let's see if this works. So here's an example of a subaerial landslide in Alaska that generated a tsunami. Oh, you guys probably aren't seeing the video because I shared the PDF, maybe?
No, we're not seeing that one.
Oh, okay. I'll skip past that. But anyway, there's a really cool animation you missed. I'm just kidding. But anyway, the simulation you weren't able to see was of this landslide here, which sits above this fjord. The landslide, this happened in 2015. The landslide flowed into the body of water. Here's a cross section. So we have the landslide source material that flowed into the water and generated waves. So how would we set this up in DClaw? Well, it's just a matter of initializing all these variables. And so again, we would initialize the landslide surface with the DEM like before, but then we would also now initialize the landslide solid volume fraction. This might just be a file that has one value for M, for instance, but that's necessary because we also then would want to initialize the lake or the fjord or water body with a different DEM and a different solid volume fraction. So I would, in that simulation, I would have another DEM here, which I'd read in the same way as the landslide top surface, except it would specify the fjord. And it would, in this case, just be a DEM with a constant value, but the DEM would specify the region where this water body is. And then we would use another file to initialize the water, which is just solid volume fraction equals 0. So notice here I would have QI equals 4, which is HM. But for convenience, it's typically you would know the solid volume fraction M, not HM. And so in DClaw, setting this component here, QI, to 4 would interpret whatever file you have as the solid volume fraction M, and then HM would be initialized using the depth there. So this is moving on to another type of application, and that's where we have a landslide and a body of water. And then, so this is an example at South Sisters in Oregon. There's a hypothetical landslide which hits this moraine dammed lake, generates waves, and then those waves overtop an earthen dam, and then that flow entrains this bed below it, entrains the material. And so we can do entrainment in DClaw. It's one of the newer things I've been working on. And that entrainment, here's a same simulation showing the landslide generate the waves. And if you look closely, you can see that this bed is eroding down, and that substrate material is going into the flow. And so this can be done with water that's flowing over erodible material, or a debris flow that's flowing over erodible material, and that solid material below and the water are being incorporated into the flow. So I have some high-tech graphics here to show how this would be done in DClaw. So we've got the surface elevation like before and the depth, and this could be pure fluid or debris flow. And then we have this layer here below the flow, which I've called A, which is the erodible material that can be entrained. So our basal elevation here now I've still called B, and it's originally just a function of X and Y, but that could evolve if this material is eroded. And so in this example, notice now this material that we initially set up is carved out from the flow. This goes into the flow above it, and we've now eroded this material here, this delta A. And so in DClaw, you can initialize this variable A, which this refers to, maybe I didn't make this clear, this refers to what you're considering any material that can erode. So below this line here, this is considered bedrock or can't be eroded. And you might have a map which defines that bed material that can be eroded. And we would initialize that auxiliary variable for that erodible layer just similar to the other variables. And it's an auxiliary variable, which you might be familiar with in GeoClaw. And it's similar syntax here. You would just specify the type of file that's your DEM file. And then it just so happens that the auxiliary variable which defines this layer is 5 in DClaw, and you set these other parameters similarly. And then you would just read in this auxiliary file, which would populate an auxiliary array, which defines that. I'll back up just briefly. This notice our bottom bathymetry here, or topography, has changed as we've eroded this away. And so this needs to be kept track of, this delta A everywhere, and that happens to be it's used in the Q array. It's one of the Q arrays in DClaw. but it doesn't need to be initialized because it's initially 0. Maybe in the future there'll be more flexibility where that could be more read in more variably. I think let's see, I'm kind of pushing the time limit here. I'll just briefly mention that AMR is controlled a little bit differently in DClaw. I use something that I called flowgrades, for lack of a better term. And what this does is basically sets up how, how you want refinement to occur. And so you can look at the details later and ask questions to me if you have them. But the idea is that you specify some value here, and you choose your variable you want refinement to be based on. So that might be the depth or the velocity, etc. I've got this parameter here is called flowgrade type. That's just whether you want to look at the norm of that solution, so the total depth, or you might want to look at the gradient and the depth. And the way it works is you set a value for a variable. This says whether it's the norm or the gradient, and then you say if that threshold is crossed, refine to this level. So in this example, it says if the velocity is very low, so if the flow is moving at all, we'll refine to the highest level, and so on. There are also a number of material parameters that are set up in DClaw, and I won't go through the details, but you would see them in a set run file. And so, for instance, different the friction angles and so forth, and you can set an initial solid volume fraction if you're not using a DEM file to initialize that. So that's what this is here. This would be an example where we have a landslide material that's about 60% solid. And there's other material parameters, which I won't go into the details. And that's all I have. Again, the code's still sitting here at this GeoFlows repository. And there's an application repository as well. And later, if people are interested in trying it out, free to help out with how to set that up.
Great, thanks, Dave. There was a question from someone about whether the Tan Fjord case is available online, but also maybe you could try sharing that other app right now and see if you can use it to play if you want to.
Oh, okay. And is it possible? The question was simulated tsunami generated by a lahar. Yes, it is, or a landslide. I'll try to. Oh, are you guys still looking at my PDF? I'll do stop sharing and then share screen again. Let's see. So do you see that?
Yes, yep.
Okay, so yeah, here's the landslide. This was, I think, about a 80 million cubic meter landslide that happened near Tyndall Glacier. No one witnessed this, but it was detected through seismic inversion. And then later, they've done a lot of field work up here to sort of reconstruct what happened. But we raise the fluid pressure here. Eventually, it fails and then generates the waves. And then have quite a few movies of that same. That was just zoomed in on the source, of course, and it generated a tsunami which traveled outside of the fjord and into Icy Bay. Quite a few different movies of that. If later someone's interested, I could try to share those somehow. And also I see some questions. I'll point out. I'll try to get these slides available. They're kind of big right now, or the PDF is large, but I'll maybe strip out some of the stuff and make it available. But I see a question from Francis that says, in the entrainment mode, is that based on grain size or some type of roadability? So not currently, other than, and the entrainment models are fairly new. So that's one of the things we're working on to get different types of entrainment models. There's one parameter, a coefficient, which is kind of a fudge factor, which just, you can choose how easily this material is entrained. Connecting that to a particle size, we don't have anything quite that that vigorous. But that's the idea of that coefficient, is it somehow reflects how easily the material can be entrained. And right now, I should point out the material that is entrained from the bed into the flow. Right now, there's not a way to specify variable porosities of that material and variable particle sizes, which I think would be nice in the future. But right now, it's just fixed to be the same as the landslide material, or using default parameters. So those are features we'd like to add in the future. And it looks like yes, from Katie. Okay. And then I see another one. Why is A of X also not dependent on time? Right. So the array A of X and Y refers to the initial amount of material that can be eroded. And so as that layer erodes, it is dependent, but what I used as A, that what you read in at the start, refers to just the initial amount of material that exists there. So it doesn't depend on time. But by using this other variable delta A, or it happens to be Q7 in DClaw, that lower layer does evolve in time. The bottom of the flow evolves in time, but it's this A minus the delta, or plus the delta A. So I see another question: how efficiently can the mesh be coarsened in regions with smooth flow over rough topography? Well, let's see. One could set up the flow grades to use, for instance, a gradient, the gradient in the solution to base the refinement parameters on that. So in terms of efficiency, how efficiently, yeah, that would just depend on the efficiency of the code with the AMR. But in terms of accomplishing that could be accomplished with that flow grade way of setting up your refinement criteria. Typically for debris flows, I almost always am using a single refinement grids level for anywhere where the flow is happening. Although I should say, or zooming into a location that you're interested in where it would refine to a higher level because you're interested in that location. But I typically haven't experimented too much with using different levels based on the gradients in the flow and so forth. But it can be done.